Okay, then I think we'll continue with the last session. There will be 3 speakers because it doesn't make sense to have the coffee break just before lunch. So we'll aim for a lunch at 12:02 with 3 talks of 20 minutes exactly. The first off is Abhishek Gupta. He is also affiliated with ICDT and helps us to advance cybersecurity at OSU. And today he's talking about model-free attack detection in complex autonomous systems. Thanks a lot.
Thank you, Felix, and thank you for inviting me for this particular conference. Very interesting. So, what I am going to talk about today is when we have complex autonomous systems, how exactly can we come up with attack detection algorithms? So, my research group essentially works on the mathematics of AI. So, we design a lot of TRL1 to TRL4 sort of technology for various applications. So in this particular talk, I'll be talking about cybersecurity applications that we have worked on. So there are the 2 students who have worked on this. So Johnny now is lead research engineer at GE Vernova. A lot of GE assets like, so he's building attack detection algorithms and mitigation algorithms for large 500 megawatt GE power plants. How is currently a student at OSU, but he's graduating this month and he'll be joining Meta next month. And he'll be using the algorithms that we have designed to sell you shoes, clothes, whatever, t-shirts and things like that once he joins Meta next month. This research was supported by Cisco and Ford. So thank you for them. So now, this is the abstraction of an autonomous system. So we come from a control theory background. So what we always talk about is there is a plant, there is a sensor, there is an actuator. And then the sensor measures some information about the plant. So think of this building as a plant. The temperature sensors are measuring the temperature. I think there is a thermostat right here and all across this room. So they are all measuring the temperature of the room. It's sending via communication channel, which would be a wired channel in this particular building, to some central unit, which is doing the estimation of the temperature, detecting if the true temperature is different from the estimation of the temperature, figuring out how much cold air, hot air to blow through many air handling unit within this building, and potentially also learning something about the system. For instance, there is a conference going on, so the amount of heat that needs to be rejected from this room has to be much higher. So it's learning all of that, sending the control signal back from the communication channel to the actuator. The actuator here would be the air handling unit. You can see a bunch of vents all over the place, which is sending cold air into this particular room, and that's changing the temperature of the plant. So what we see here is there is a very nice intersection of control, computing, and communication. And what we tend to work on within our group is to work on these 2 aspects in order to detect the attack and do robust estimation. One of the things that many people have talked about is information security, but the problems that we face in autonomous system like this building is that information security is not enough. So you can think of information security as the first wall which dodges a lot of bullets, right? But then you also need to do attack detection. So somebody was able to get into the system, so we need to detect the attack, and then we need to come up with algorithms that mitigates the attack. So our group basically works on these 2 walls, creating these 2 walls. So the reason why these information security notions will not necessarily work for autonomous systems, like it works as the initial preventive measure, but then if the attacker is able to get through that particular preventive measures, then we need to figure out, we need to exploit all the information we know about the system in order to detect and mitigate the attack. So one of the things that we need to worry about in autonomous systems is that there are many feedback loops that are internal to the system. We don't really observe it. There is changes in the model and environment. So in the morning, 8 o'clock, this room was completely empty. At 11 o'clock, now this room is completely full. So there has been change in the model and the environment for this particular system. There's partial observability. And then we also need to do resilient and robust estimation. So those are the things that we worry about for the autonomous systems. So what are the challenges? Like I mentioned, the system components degrade over time. There are repairs that are being done to the system. So think about this building. The building was commissioned back in 2016, 2017, and some air conditioning unit, some air handling unit might have gone bad, might have had some repairs. So the system is constantly changing. And what happens when the system is changing is we cannot really model the system every time something gets changed, something gets repaired, something gets replaced. We don't really have the time to model this entire building. And if we want to come up with attack detection and mitigation strategy for this building, the traditional attack detection algorithms requires the knowledge of the system, and we want to get rid of that constraint. So we don't want to have model knowledge because there are lots of repairs happening all throughout the time. And then, of course, the external environment also changes over time. So right now, the outside temperature would be, let's say, 65, 70 degrees Fahrenheit, but at night, it might go down to 40 degrees Fahrenheit. So the external environment is also changing over time. So really the question we asked ourselves back in 2019, 2018, 2019 is how do we detect and mitigate attacks without the knowledge of the dynamics of the autonomous system? So with knowledge of the dynamics, there are a lot of algorithms in the literature, but without the knowledge, there are very few set of groups that are working on this particular problem. So we made several contributions in this area, but I'm going to talk about the most pertinent to this particular group, which is model-free change point detection. That's what I'm going to be talking about today, but happy to talk about other topics after the presentation. So suppose we have yesterday's data from the building, we have today's data from the building. Do they look statistically the same? So that's the test that we are designing. And if they don't look the same, then attack is detected. If they look the same, then there is no attack in the system. So what we are trying to do is create statistical tests and imbibe in them a model constraint so that we are able to detect the attack in a reasonable time frame. The second contribution we made was dynamic watermarking for autonomous systems. So here, basically, the idea is that the controller is going to add small signal to the control signal that whose realization will not be known to the attacker. And so the detection algorithm is going to see whether the information that they are getting from the sensors are authentic or not. So they can actually authenticate the information coming out of the sensors by using the fact that this information, that the small signal that the control policy added is known to the detection algorithm, but it is actually unknown to the attacker because the attacker cannot see it. So we call this dynamic watermarking, and we developed an algorithm for dynamic watermarking for autonomous systems. And then we have looked into several applications. We have designed an algorithm for puff authentication. We've designed quick exchange detection for Markovian systems, and we've designed Byzantine resilient algorithms for machine learning, for federated learning systems. So let's talk about the first topic, which is model-free change detection algorithm. So this is the mathematical problem. So we are given two data sets, x1 to xm, which is generated from an unknown Markov kernel P. By unknown, what I mean is this is the data set from yesterday. So so x1 is the sensor reading from all the temperature sensors within this building from yesterday. And we don't quite know what the building model is. All we have is this data set. We have logged the data set from yesterday, and we have this log data set of all the temperature readings from this building from yesterday. And right now, the temperature readings of this particular building is getting generated. And we again don't know what the model of the system, today's system is. Okay, now if there is no attack, then the yesterday's system and today's system are going to be the same. If there is an attack, then today's data set will come from a different statistical distribution, and we want to be able to detect that particular change. So the eventual mathematical goal, mathematical formulation is we need to design an algorithm that takes into account these two data sets and detects whether P is equal to Q or not. So these Markov kernel they are the same or they are different. Okay, so the way we view it is yesterday's building data is unattacked because we know that there was no cyber attack, everything was working fine. So yesterday's data is unattacked dynamical system data, and Q is the current dynamical system, and it may be attacked, it may not be attacked. So that's what we are trying to detect. So the way we solve this problem is use this notion of maximum mean discrepancy. It's a mathematical tool that was designed. It was designed back in 1950s, but people started using it more often since 2005, 2010. So we used this tool, this mathematical tool for this particular algorithm design. So what we do is embed the stationary distribution and Markov kernel into what is known as a reproducing kernel Hilbert space. Then we use data to identify that particular element of reproducing kernel Hilbert space, which corresponds to the stationary distribution cross Markov kernel. And the change detection problem then becomes distance between these two elements of reproducing kernel Hilbert space. So you can think of it as this way. This is my distribution P, this is my distribution Q. I'm going to embed it into RKHS, and now the distance between these two elements is going to give me an idea about whether these two distributions are the same or these two distributions are different. So that's what we are trying to do here. So the way maximum mean discrepancy is defined is you defined a kernel function over the state space. So there are many different types of kernel functions used in the literature. And it can be used for various different variables. So for instance, if you have integers, you can have a specific kernel function. If you have categorical data, you can have a different kernel function. And if you have d-dimensional objects or angles, you can have different kernel functions. So various kernel functions are already known. And this is a valid distance. So if two distributions are the same, MMD is going to be 0. If the two distributions are different, MMD is going to be different. So it turns out that we can compute the empirical MMD using data alone. We don't need to know the model of the system. So remember, we had the data set from yesterday. We have the data set from today. I'm going to construct second order Markov chain, and I'm going to define empirical measures over the second order chain. And it turns out that the MMD between the two distributions are going to be close. It can be approximated by MMD between these two empirical distributions. So that leads us to this model-free change detection algorithm. So here it's a lot of mathematical stuff that How has worked on, How is sitting in the audience. So all the questions can be directed to him after the talk. But this is basically some, based on whatever data you're receiving right now, you can construct this particular, you can compute this variable, and then you take the max over all different variables that you have seen so far. And then if the max is greater than a certain threshold, then you raise an alarm. So that's roughly what the algorithm is. So what we are seeing is this is the reference data from yesterday. This is just a mathematical simulation on Python. So this is not coming from a real data, real world data set. So we have this reference data from yesterday. We have the new observations coming in at today, and you can see at time t equals to 1000, the attack was launched. The statistics of the entire system has changed after the attack was launched. And then our algorithm was able to detect that over time. So depending on where your threshold is, let's say you made your threshold to be 30, then at 1500 seconds, you will be able to detect the attack. If you want to learn more about some of the tools and techniques we have developed or our community has developed for detecting autonomous systems, you can take a look at the course EC 5555 that's available on YouTube. It has been viewed 674 times, so you can be the 675th viewer of this particular set of lectures. So feel free to explore it. If you have any questions, feel free to reach out to me. So that's all I have for today's discussion. So we talked about this particular problem where we look at different data from yesterday and today, and we can decide whether an attack has happened or not. Alternatively, I mean, not alternatively, but the other problem that I'm happy to talk about would be the dynamic watermarking algorithm. We have not talked about it in the presentation, but happy to talk about it offline. And if you want to reach out to me, feel free to send me an email at this email. Thank you. Yes, please. So, right. Yes, yes, that's all in the paper. Yeah, yeah. So those things depends on the ergodicity of the Markov kernel. So there's a lot of parameters that gets into those expressions. But we have characterized mean time between false alarms and the time to detection, the mean time to detection. I think so. So I think what you are referring to is known as causal inference. So we don't really we did not work on the causal inference of what's causing the attack, and then therefore we can talk about the severity of the attack. It So some of the tools can be used for doing the causal inference stuff as well, but we don't do it in the paper. And more importantly, causal inference requires order of magnitude more data. So then the question becomes, do we really have that kind of data set? And then you have to be very focused on a specific system. So these are sort of general purpose algorithms. You can apply it to blood pressure monitoring. You can apply it to disease detection. You can apply it to cyber attack detection, whatever. But when it comes to causal inference, you need to know if you're figuring out attack on this particular building, and then you have to build the causal model of the building, and then you can do all that rest of the stuff. Something that I'm interested in, but there's no funding to work on these problems, so I'm not able to work on this. Yes, please. Right, right, right. So yeah. So at a mathematical level, all of these areas are very similar from a mathematics point of view. So whatever you mentioned about quality control, so there are statistical tests for quality control. Now, the problem that happens in those tests is a lot of quality control algorithms are again based on the model of the system. Like you need to know what the model is, and then you can do quality control on top of it. You can come up with detection algorithms. What we are doing here is we don't want to know the model at all because things are changing continuously. Somebody is going to come tomorrow, there will be a ticket raised. They'll come and fix whatever air handling unit here, turn off the air handling unit there. And so now the problem is the model has changed and we don't really want to model the system all over again. Yeah. Thank you. All right. Yeah. Yes, please. I'm not, but that's just easy to explain to people. Yeah. Yeah. Right. Yes. So this data is actually generated from the dynamical system. So this is the data. This is the temperature data at, let's say, 12:01 p.m., 12:01 a.m., 12:02 a.m., 12:03 a.m., and so on and so forth. So that's the whole point, that we don't want to go through the model dynamics itself. So every day we'll have a different model of the system. We could have a different model of the system. So to give you an example, there are windows here, and the windows have some airflow coming in, going out, depending on what the outside temperature is. It could be colder, hotter. So the whole thing is changing every day. Of course, since yesterday, the weather hasn't changed much, but since January, the weather has changed a lot. And so all of that comes into picture when you're designing the statistical test. So if we had created a model in January and a lot of things have changed, then the test today is going to raise a lot of alarms, because we have developed the model from that particular month. Yeah. Thank you so much.